I want you to start by doing something very simple. I want you to look at your hand.
Am I?
Just hold it up and look at it. You see skin, knuckles, maybe a hangnail or a scar. It looks solid, right? A biological object. But if you were to take a pin and prick the tip of your index finger right now, you know exactly what would happen.
Oh, yeah. You'd pull back
Yep.
immediately, but before you even consciously processed what was happening.
Right. And then a split second later, the sensation would hit you. The sharp sting, the throb, the annoyance.
Yeah.
We spend our entire lives running away from that sensation.
We do. We design our shoes, our chairs, our entire civilization to minimize that feeling.
It is the universal negative reinforcement.
It's the body's way of shouting, stop.
Exactly. So imagine if I told you I could take it away. I could flip a switch in your DNA and you would never feel that ouch again. You could walk across Legos in the dark and feel nothing.
You could grab a hot pan and just hold it.
It sounds like a superhero origin story.
The Man of Steel or the Woman of Iron. But when we actually look at the data, and specifically the source material we have today on sensory processing, we see that this superpower is actually a horrifying biological trap.
We're talking about the case of Ashlyn Blocker. And looking at the notes here, her story is the perfect entry point into the machinery of human sensation. Because Ashlyn is a girl who, biologically speaking, has no check engine light.
That's a great way to put it. Ashlyn was born with a condition called congenital insensitivity to pain with anhidrosis.
Wow.
It's incredibly rare. And to understand the gravity of this, you have to look at the stories from her infancy.
The diaper rash story stuck with me. It's so mundane, but in this context, it's terrifying.
It is visceral. Most parents know their baby has a rash because the baby screams. The pain is the communication. Ashlyn didn't cry.
Nothing.
She had raw, irritated skin, severe inflammation, but she just lay there looking around, smiling.
And it escalates. The source material mentions that when she started teething, she didn't just chew on toys.
No, she chewed on herself. She chewed off a portion of her tongue because she lacked the feedback loop that says, stop, you are destroying your own hardware.
Because she didn't get the negative signal.
There was another incident where she scratched her cornea deeply, and nobody knew until her eye was swollen and bloodshot because she didn't feel it.
And then, as a teenager, the story that really defines this condition for me, she dropped a spoon into a pot of boiling pasta water. And what do you do if you drop a spoon? You might hesitate, grab a mitt, or fish it out with tongs. Ashlyn.
She just reached her hand right into the boiling water to grab it.
Just like that.
Reflexively. Because her brain never learned that boiling water equals danger.
She burned her skin, but she didn't feel a thing. And that brings us to the central theme of today's deep dive. We are looking at Chapter 8 of Behavioral Neuroscience, which covers general principles of sensory processing, touch, and pain. And looking at Ashlyn, we realize pain isn't just an annoyance, it's a navigation system.
Precisely. Ashlyn can be damaged just like anyone else. Her skin burns, her bones break. She just doesn't get the warning signal.
Right.
So her life is actually incredibly perilous. She has to intellectually monitor her body for damage that you and I would detect instantly through sensation.
So here is our mission for this deep dive. We are going to deconstruct that machine. We aren't just going to list the parts. We are going to trace the signal. We want to know how the physical energy of the universe, heat, pressure, light, gets translated into the electrical language of the brain.
It's called transduction, and frankly, the engineering involved is mind-blowing.
I can't wait.
We're going to cover how your skin is basically a battery waiting to be discharged, why peppers taste hot when they aren't, and the bizarre wiring of the spinal cord that explains why a heart attack hurts your left arm.
Let's get into Section 1, General Principles of Sensory Processing.
Right.
And we have to start with the hardware, the sensory receptor organs.
Right. Every animal has these specialized body parts: eyes, ears, skin receptors. Think of them as filters.
Filters.
Yeah. The world is full of energy electromagnetic radiation, sound waves, chemicals, magnetic fields, but we only detect a tiny slice of it. Our receptor organs filter out the noise and capture what's relevant for our survival.
And we call the thing that triggers these organs a stimulus.
Correct. A stimulus is just a physical event.
Yeah.
A sound wave, a photon of light, a chemical molecule in your food.
The text has these amazing images in Figure 8.1 showing the diversity of these organs. It really highlights how different species have different survival strategies.
It does. Figure 8.1 put four very different eyes side by side. You have the compound eye of a black fly.
Which looks like a grid of tiny lenses, almost like a honeycomb or a pixelated screen.
Exactly. It's not a single coherent image like we see. It's a mosaic. Then you have the panther chameleon with eyes that move completely independently.
Oh, right. One looking forward, one looking back.
Which would be incredibly disorienting for us. Imagine trying to walk if your left eye was looking at the floor and your right eye was looking at the ceiling.
It would be nauseating.
But for a lizard that is both a predator and prey, it's perfect. One eye scans for food, the other watches for threats.
And the others.
Then there's the Philippine tarsier, which is this tiny primate with absolutely massive eyes specialized for night vision. And finally, the bald eagle, which has incredible visual acuity for spotting prey from high altitudes. The point is, the shape and function of the receptor organ, the eye, dictates what that animal can see.
And it's not just about what we can see, but what we can't. The text mentions hidden senses, like bats.
Bats are a classic example of how limited our own perception is. Humans can hear sound frequencies up to about 20,000 hertz. That's our biological ceiling.
That's it.
But bats, they're operating in the ultrasonic range, 50,000 hertz and above. They are screaming through the sky, hunting moths using biological sonar, and to us, the night is silent.
Wow. And snakes.
Some snakes have specialized organs in their faces pit organs that detect infrared radiation. They can literally see body heat.
So in pitch darkness.
A warm mouse glows like a light bulb to a snake. To us, it's just dark.
This concept really touches on the idea of the umwelt, the self-world. Our reality is defined strictly by what receptors we happen to have.
Exactly. We are trapped in the bubble of our own sensory hardware.
That brings us to a key term in the text, the adequate stimulus, which sounds like a backhanded compliment. You're an adequate stimulus, I guess.
Yeah, it does. But in neuroscience, adequate is used in the older sense of appropriate or matching. It's the specific type of energy an organ is adapted to.
So the adequate stimulus for the eye is light energy.
And for the ear, it's sound pressure.
But the text notes you can cheat the system.
You can. The text gives the example of phosphenes. If you get punched in the eye or if you gently press on your eyeball with your finger in the dark, you see stars or flashes of light.
Right, I've done that. Don't recommend the punch, but the pressing works. You see these geometric patterns.
What's happening is that the mechanical pressure is stimulating the retina. The retina is supposed to respond to light, but if you hit it hard enough, the neurons fire anyway. But here's the key. Because those neurons are wired to the visual cortex, the brain interprets that signal as light.
The brain doesn't know you poked your eye. It just knows the eye wire is active, so there must be light.
Exactly. Mechanical pressure isn't the adequate stimulus, but it can still trigger the system. It just confuses the hardware.
This leads perfectly into a historical concept mentioned in the chapter, Johannes Müller and the doctrine of specific nerve energies.
This takes us back to the 19th century. Müller was trying to figure out exactly this problem. How does the brain know the difference between a sound and a flash of light?
Right.
He proposed that the nerves themselves must carry different types of energy, like maybe auditory nerves carry sound energy and optic nerves carry light energy.
But we know now that's wrong.
Completely wrong. And this is the fundamental reveal of neuroscience. All nerves carry the exact same thing.
Action potentials.
Yes, it's all just electricity.
It's all just sodium and potassium rushing in and out of cells.
It's all electricity. Whether you are seeing a sunset, hearing a symphony, or smelling a rose, the signal in your brain is identical. It is a series of electrical spikes.
So if the signal is the same, just a spark, how does the brain know this is a smell and this is a touch?
That is the concept of labeled lines, illustrated in figure 8.3. Imagine a bundle of cables running into a control room without windows. The electricity running through the cables is identical, but the operator knows that cable A comes from the security camera and cable B comes from the microphone.
So the meaning is defined by the path.
Exactly. If a neuron in the touch pathway fires, the brain says, I feel something. If a neuron in the visual pathway fires, the brain says, I see something. Even if, like with the eye punch, the signal was triggered by the wrong thing.
The brain trusts the cable label, not the source.
You got it. And this goes even deeper than just the five senses. Figure 8.3 shows that even within touch, we have separate labeled lines for light touch, vibration, and stretching.
It's not just one touch signal.
Right. Your brain gets separate streams of data. One line says, this is vibrating. Another says, this is stretching my skin. And a third says, this is painful. The brain acts as a synthesizer, combining these independent tracks into a cohesive experience.
Let's talk about how that spark gets started.
Yeah.
The text introduces a term here that sounds like a sci-fi protocol. Sensory transduction.
It does sound technical, but it's the fundamental miracle of perception. Your brain lives in a dark, silent box, the skull. It never touches the world directly. It only knows action potentials.
So transduction is the translation.
It's the currency exchange. You're
Yeah.
swapping physics for electricity.
Okay, so how does it work? The book uses the Pacinian corpuscle as the model for this.
The gold standard model, yeah. And I'm looking at figure 8.4. It looks like an onion.
It really does.
It's a nerve ending wrapped in layer upon layer of connective tissue with fluid in between. It's buried deep in your skin. Now imagine you press your thumb against the table.
Okay.
You are physically squishing that onion.
Okay, so I'm deforming the shape.
Right. That physical deformation travels through the layers and actually stretches the membrane of the nerve fiber inside. Now, here is where we have to zoom into the molecular level.
All right.
The skin of that nerve fiber is studded with little gates.
These are the ion channels.
Specifically, mechanically gated sodium channels. Think of them like a tent flap that is tied to the tent poles.
Okay.
If you stretch the tent, the flap pulls open. When you squish the Pacinian corpuscle, you stretch the cell membrane and you physically pull these molecular pores open.
And since the neuron is floating in a salty soup.
Sodium ions, Na+, rush in. Now, we need to pause here because this is a concept people often gloss over. Why does the sodium rush in?
Because there's less of it inside.
That's half of it. That's the concentration gradient. But the inside of the neuron is also negatively charged compared to the outside. Sodium is positive.
Opposites attract.
Opposites attract. So you have this massive electrochemical pressure. Sodium is desperate to get inside that cell.
It's not just drifting in, it's being sucked in.
Violently. So you press your skin, you stretch the membrane, you pop open the door, sodium floods in. This creates a small electrical change called a generator potential.
But that's not the signal sent to the brain yet, right?
Not yet, and this is a crucial distinction in the text. The generator potential is analog. It's like a dimmer switch.
Wait.
If you press a little sodium comes in, the voltage goes up slightly. If you press hard, a lot comes in, the voltage goes way up.
But the brain only speaks digital. It only speaks fire or don't fire.
Precisely. The neuron has a threshold. The generator potential has to get high enough to trigger the main event, the action potential. If that little sodium influx hits the magic number, usually around megas for 40 millivolts, then boom, the whole nerve fires and the signal shoots up your arm at 70 miles per hour.
So if I touch something very lightly.
You might create a generator potential that is too small, it fizzles out, the sodium pumps kick it back out, and the brain never hears about it. It effectively didn't happen.
That is wild. My reality is literally determined by whether I can squish this onion hard enough to hit a voltage threshold.
Every moment of every day.
Okay, so we have the signal. Now the brain has to process it. The chapter lists 6 key aspects of sensory processing. Let's run through them because they give us the vocabulary for the rest of the deep dive.
Let's do it.
Number 1 is coding.
Coding is how the brain understands the details. The neuron fires, but how intense is the stimulus? Is it a feather or a hammer? Since action potentials are all the same size, you can't have a bigger action potential. The brain uses frequency.
Like Morse code.
Sort of. It's about rate. A light touch might be pop, 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 pop. A heavy smash is pop, 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 pop. More spikes per second equals more intense stimulus.
The text also mentions range fractionation, which sounds like a math problem.
It's actually a brilliant biological strategy. Imagine a choir. If you only had one singer, they couldn't hit all the notes from low bass to high soprano.
Right.
Range fractionation means having different neurons specialize in different intensities.
So you have low threshold neurons.
That fire at the slightest touch. And you have high threshold neurons that only wake up when you really smash your finger. By combining them, the brain can measure a huge range of pressure, from a gentle breeze to a crushing weight.
Got it. Number 2, adaptation. This is the getting used to it phenomenon.
Right. Figure 8.7 illustrates this perfectly. It shows a neuron firing rapidly when a stimulus starts, but then slowing down even though the stimulus is still there. This is why you feel your clothes when you first put them on, your waistband, your socks, but 5 minutes later you don't notice them at all.
And thank goodness for that. If I constantly felt every thread of my socks all day, I'd go insane.
Exactly. Adaptation prevents information overload. It allows the brain to ignore the constant stuff and focus on changes.
And the text makes a distinction here between types of receptors.
It does. We distinguish between tonic receptors, which show little adaptation, they keep firing to remind you, hey, this is still here, and phasic receptors, which adapt rapidly.
Okay, so phasic is for the close, tonic is for what? Maybe the feeling of the ground under your feet when you're standing.
That's a good example. Something you need to be constantly aware of for posture.
Number 3 is suppression.
This is active dampening. Sometimes we need to turn the volume down. This can happen at the source like closing your eyelids to block light, or the tiny muscles in your middle ear tightening to dampen loud sounds before they damage the cochlea.
Or top-down processing.
Yes. This is the brain sending signals back down to the lower levels to say, ignore that. We see this in pain inhibition, which we'll talk about later. It's the brain deciding what matters.
Number 4, pathways.
The roadmap. For most senses, the signal goes from the receptor to the spinal cord or brainstem and then to the thalamus.
The thalamus.
It's at the great relay station of the brain. It directs the traffic. From there, it goes to the cortex.
With the exception of smell, right?
Right. Smell is the ancient outlier. It bypasses the thalamus and goes straight to the emotional centers, the amygdala and hippocampus. This is why a scent can trigger a vivid memory or emotion instantly before you even identify what the smell is.
Ah, that makes sense.
But for touch and pain, thalamus first.
Number 5, receptive fields.
This is the specific area of space that a neuron cares about. Imagine drawing a circle on your hand. For a touch neuron connected to that spot, that circle is its receptive field.
And if you touch outside that circle.
That specific neuron won't fire, simple as that.
And finally, number 6, attention.
The spotlight. We can consciously choose to focus on specific stimuli. If you are in a crowded party, you can choose to listen to the person in front of you and tune out the background noise.
And we can see this in the brain.
Yes, the text points to figure 8.12, which shows brain scans. When we are paying attention, regions like the posterior parietal cortex and the cingulate cortex light up. We are priming the brain to receive specific data.
Speaking of the cortex, we have to talk about the map, the somatosensory cortex, and specifically the little man, the homunculus.
Figure 8.10. It's a classic image in psychology and neuroscience. If you drew a human body based on how much brain power is devoted to feeling each part, you get the homunculus.
And he looks ridiculous.
He does. He has absolutely enormous hands and gigantic lips and tongue, but his trunk and legs are tiny. He looks like a cartoon character.
Why? Why the distortion?
Because receptor density is not uniform. Your fingertips are packed with receptors for fine detail. Your back, not so much.
You can test this, right?
Easily. If someone pokes your back with 2 pencils an inch apart, it might feel like one poke. The receptive fields are huge and overlapping. Do that on your lip and you'll definitely feel 2 distinct points. The brain map reflects that sensitivity.
It's not a map of your body, it's a map of your sensation.
That's the perfect way to put it.
And it's not just humans. The text gives us the example of the star-nosed mole in figure 8.11.
I love this example. The star-nosed mole is nearly blind. It lives in dark tunnels. But it has this nose with 11 fleshy rays or tentacles that it uses to touch everything.
How fast?
It touches objects 12 times a second.
Wow.
And its brain map, its somatosensory cortex, is almost entirely devoted to that nose. It has a massive cortical representation for the nose, specifically the 2 bottom rays, which act like a fovea or a center of focus.
So it sees with its nose.
It absolutely sees with its nose. It's the same principle as the human hands.
Yeah.
You devote brain space to what matters for survival.
And these maps aren't set in stone, are they? The text mentions plasticity.
No, they can change. If you lose a finger, the brain space for that finger doesn't just go dark. The neighboring areas, the other fingers, will encroach and take over that territory.
And for musicians.
Or if you're a musician and you use your left hand intensively for violin, the representation for those fingers will actually grow in the cortex. The brain is constantly rewriting its own atlas.
Before we move to the specific mechanics of touch, there's a box in the text box 8.1 about synesthesia. This is when the wires get crossed, right?
In a way, synesthesia is a condition where a stimulus in one modality evokes a sensation in another. The most common is seeing numbers or letters as having specific colors, like the number 5 is always red.
For them.
For them, yes. Or hearing a specific musical note creates a taste in the mouth.
And this isn't a metaphor. They literally see the color.
Yes. The text mentions that they likely have polymodal cells in the association areas of the brain that are mixing these inputs. It shows that our perception of separate senses is really a construct of how our brain separates the lines. For synesthetes, the lines are a bit more porous.
Let's move to section 2. Touch. We talked about the Pacinian corpuscle, but the skin is actually packed with 4 different main types of receptors. Figure 8.3 lays them out.
Right, we call them the tactile receptors, and they are categorized by 2 things: what they detect and how fast they adapt.
Okay, let's run through the roster. First, the Pacinian corpuscles we met earlier,
They are large, they are found deep in the skin, and they are fast adapting.
meaning they fire when a stimulus starts and stops.
Right. They are perfect for detecting vibration and texture. They are your earthquake detectors.
Next, Meissner's corpuscles.
Also fast adapting, but they have smaller receptive fields. They are good for light touch and detecting changes in form.
Then Merkel's discs.
These are slow adapting. They keep firing as long as the touch is there, and they have small receptive fields. This makes them the kings of fine detail.
So reading Braille, for instance.
If you are feeling a sharp edge or a tiny bump, that's your Merkel's discs working. They are the architects.
And finally, Ruffini's endings.
Slow adapting, but with large receptive fields. They detect stretching of the skin. So when you move your fingers or grasp an object, Ruffini's endings are telling you how your skin is being pulled over your muscles.
There's a really cool example in figure 8.42 about reading Braille. It compares how these receptors fire.
This is a crucial study. Imagine the graph. They recorded from these receptors while a finger moved over Braille dots, the Pacinian corpuscles. The readout is just a mess, a blur of activity.
They can't make out the dots.
They picked up the vibration of movement, but they couldn't distinguish the dots. They're too sensitive to the vibration. They see the forest, but miss the trees.
And the Merkel's discs.
The Merkel's discs. Their firing pattern looked exactly like the Braille dots. A perfect, faithful representation of the form. That's why we use our fingertips to read Braille. They are packed with Merkel's discs.
Now, once these receptors fire, the signal has to get to the brain. And for touch, it travels fast.
Very fast. Touch uses what we call a beta fibers. These are large diameter axons, and they are myelinated.
Myelin is that insulation wrapper, right?
Yes. In physics, a wider pipe and insulation means less resistance and faster speed. A beta fibers conduct signals at about 35 to 75 meters per second. It's a superhighway.
Okay, we've generated the spark. Now we have to get it to headquarters. The text contrasts 2 major highways for this: the dorsal column system for touch and the anterolateral system for pain.
And listeners, if you are driving whilst listening to this, don't zone out here. This is one of the most elegant and confusing pieces of engineering in the human body. The wiring does not run parallel.
Let's trace touch first. Figure 8.15, I touch a velvet couch with my left hand.
The signal shoots up your left arm into your spinal cord via the dorsal root. And here's the key. It stays on the left side.
Okay.
It travels up the dorsal column, the back part of the spinal cord expressed to the brainstem.
So far, so good. Left hand, left side of the spine.
But when it hits the medulla, the brainstem, it synapses on a neuron there. And this is the crucial moment. The axon from that medulla neuron crosses the midline to the right side.
So the crossover happens in the brainstem, way up high.
Yes. Then it ascends to the thalamus and finally to the primary somatosensory cortex, S1. So your right brain feels your left hand. But for touch, the signal stays on the left side all the way up the spinal cord until it hits the brainstem.
That distinction, where it crosses, is going to be important when we compare it to pain later.
Very important.
One last thing on touch. Dermatomes. Figure 8.16.
This relates to the spinal cord structure. A dermatome is a strip of skin that is innervated by a specific spinal nerve.
The figure shows the body striped like a tiger or a zebra.
It does. You have the cervical dermatomes, neck and arms, thoracic chest and belly, lumbar legs, and sacral buttocks and heels.
It was very organized.
It is, and it explains clinical symptoms perfectly. If you have a pinched nerve in your lower neck, say the C6 vertebra, you might feel numbness specifically in your thumb. The wiring is consistent. Doctors use this map to diagnose exactly where a spinal injury is based on where you feel numbness.
All right, let's pivot to section 3, pain.
The mixed blessing.
We established with Ashland Blocker that pain is vital, but biologically, it's very different from touch.
Fundamentally different. We have specialized receptors for pain called nociceptors.
Nociceptors.
These are free nerve endings in the skin. They don't have the fancy onion structures like the Pacinian corpuscle. They are raw, exposed nerve endings designed to detect tissue damage.
And the text explains that when tissue is damaged, it releases a chemical soup.
Figure 8.21 shows this. When cells break, they spill their contents. Histamine, enzymes, prostaglandins, serotonin. These chemicals float over and excite the nociceptors. That's why inflammation hurts. Those chemicals are screaming, damage here.
Now, here's where it gets really interesting. How do we feel temperature? Specifically, why do chili peppers feel hot and mint feels cool?
This is one of my favorite bits of neuroscience. It's all about the TRP channels, transient receptor potential channels.
Okay, let's start with a hot one, TRPV1.
TRPV1 is a receptor on free nerve endings that normally detects painful heat. If you touch a hot stove, TRPV1 opens and you feel the burn.
Simple enough.
But it turns out that a chemical found in chili peppers, capsaicin, has the perfect shape to bind to the same receptor.
So the pepper isn't actually burning you. It's hacking the system.
Exactly. It tricks the receptor into opening. The brain gets the signal hot, hot, and you sweat, your face turns red, and you feel the burn, even though there is no actual heat damage.
And these TRPV1 receptors are on C fibers.
Yes. C fibers are thin and unmyelinated. They conduct slowly. This is responsible for that dull, throbbing, aching pain that persists after a burn.
But there's another receptor for even higher heat, TRPM3.
TRPM3 detects dangerously high temperatures, but these are found on A delta fibers. Remember A beta for touch? A delta are also large and myelinated, though slightly smaller than A beta. They are fast.
So this explains the double pain phenomenon when you burn yourself.
If you touch a hot pan, you feel a sudden, sharp OUCH immediately. That's the fast A delta TRPM3 signal. Then a second later, the slow throbbing burn sets in. That's the slow C-fiber TRPV1 signal arriving late to the party.
And on the flip side, we have coolness, CMR1.
Or TRPM8. This receptor opens when the temperature drops, but it also binds to menthol. So when you chew mint gum or use Vicks VapoRub, it feels cool because the menthol is chemically triggering the coolness detector.
It's amazing that our culinary experiences, spicy and minty, are just chemical hacks of our thermal safety sensors.
It really is. We enjoy simulating danger.
Now let's go back to Ashlyn Blocker. We know she doesn't feel pain. Do we know exactly why?
We do. And this connects back to the mechanism we discussed earlier. It comes down to a gene called SCN9A.
SCN9A.
This gene provides the instructions for building a specific sodium channel called NaV1.7.
NaV1.7.
Okay. Nociceptors, those pain nerve endings, rely heavily on this specific channel to fire their action potentials. Ashlyn has a mutation that makes this channel non-functional.
So the receptor might detect the damage, the chemicals might be there, but the neuron can't fire the spark.
Exactly. She has the hardware, the nerve endings are there, but the send button is broken.
And her touch receptors.
Her touch receptors work fine because they use different sodium channels, but her pain receptors are silent.
That is such a precise, tiny failure with such massive consequences.
It shows how specific our genetic coding is. One protein fails and the entire warning system goes offline.
Okay, let's trace the pain signal to the brain. We did the dorsal column for touch. Pain uses the anterolateral system, or the spinal thalamic system, figure 8.23.
Here is the key difference. Step 1. The pain nerve ending enters the spinal cord dorsal horn.
Okay.
Step 2. It synapses immediately on a spinal neuron.
Not going up first.
No. And then step 3. That spinal neuron sends its axon across the midline right there in the spinal cord.
Ah, so touch crosses high up in the brainstem, pain crosses immediately in the spinal cord.
Correct. Then it ascends the spinal cord on the opposite side, the anterolateral column, directly to the thalamus.
So the pain signal from my left hand is actually traveling up the right side of my spinal cord.
Correct. Touch is on the left, same side. Pain is on the right, opposite side.
This leads to that famous Brown-Séquard syndrome scenario mentioned in the clinical notes. It's a favorite of medical examiners.
It is. Imagine a tragic injury, a knife wound, or a car accident that severs exactly half of your spinal cord. Let's say the left half of the spinal cord is cut at the waist.
Okay, so the left highway is out, the right highway is clear. What happens to my left leg?
Well, the touch signal from your left leg tries to go up the left side and hits the roadblock. So you can't feel touch on your left leg, you can't feel the velvet.
But what if I stick that left leg in hot water?
The pain signal enters the spinal cord, crosses immediately to the right side, which is intact, and travels up to the brain. You would feel the burn perfectly.
That is mind-bending. I would have a numb leg that can still feel pain.
Exactly. But look at the right leg. The touch signal goes up the right side intact, so you can feel touch. But the pain signal from the right leg tries to cross over to the left side, which is cut.
So no pain signal gets through.
So your right leg is immune to pain but has perfect touch sensitivity.
It's a dissociated sensory loss.
Yeah.
It really highlights that feeling isn't one thing. It's distinct data streams routed through completely different physical cables.
And knowing that map is how neurologists can pinpoint exactly where a lesion is in the spinal cord.
Once the pain gets to the brain, it's not just ouch, it's emotional.
It is. The text mentions the cingulate cortex. This area is activated by the unpleasantness of pain. The somatosensory cortex tells you, my thumb hurts. The cingulate cortex tells you, I am suffering and I hate this.
And this leads to social pain.
Yes. Studies show that social rejection, getting dumped, being left out, activates the anterior cingulate cortex, the exact same region involved in the emotional distress of physical pain.
So when we say heartbreak hurts, neurologically we aren't being poetic.
No, we are being accurate. To the brain, the distress of rejection and the distress of a burn look remarkably similar.
But sometimes pain happens without any stimulus at all. Neuropathic pain. Phantom limb pain.
This is tragic. Phantom limb pain is when a person loses an arm or leg but continues to feel excruciating pain in the missing limb.
How can you feel pain in a hand that isn't there?
It's a case of neuroplasticity gone wrong. The text explains that microglial cells, the immune cells of the brain, in the spinal cord release chemicals that make the dorsal horn neurons hyperexcitable.
So the neurons in the spinal cord that usually report pain from the hand just start shouting on their own.
Exactly. They become chronically active. They flood the thalamus with pain signals. The brain assumes the hand must be hurting because the hand pain wire is active, but the hand is gone.
And there's that fascinating mirror box therapy mentioned.
Right. By using a mirror to trick the brain into seeing the missing limb moving and healthy, you can sometimes quiet those signals. It proves that pain is a construct of the brain, a top-down process, as much as it is a sensation from the skin.
Speaking of controlling pain, let's talk about how we can stop it. The gate control theory.
This was a huge breakthrough in 1965 by Melzack and Wall. The idea is that there are gates in the spinal cord that regulate the flow of pain signals.
And we can close the gates.
Yes. One way is through competing touch signals. If you bang your shin, what's the first thing you do?
I rub it furiously.
Why? Because rubbing activates those fast A-beta touch fibers. It turns out those touch fibers have a connection that inhibits the pain transmission cells. You are literally flooding the gate with touch noise to drown out the pain signal.
That validates every instinct I've ever had. What about drugs? Opiates?
Opiates, like morphine, work because they mimic chemicals our brain naturally produces. Endogenous opioids.
Endorphins.
Endorphins, enkephalins, dynorphins. We have receptors in our brain, specifically in an area called the periaqueductal gray, that are designed to receive these molecules. When they bind, they trigger descending pathways that close the pain gates in the spinal cord.
So morphine is just an artificial key for a lock we already have.
Exactly.
And this connects to the placebo effect.
This is one of the most important points in the chapter. The placebo effect isn't fake. It's not all in your head in the sense of being imaginary. When you take a sugar pill believing it's a painkiller, your brain actually releases endogenous opioids.
It triggers the real chemical release.
Yes. And we know this because of a brilliant experiment mentioned in the text. If you give a patient naloxone, a drug that blocks opioid receptors, the placebo effect disappears.
Wait, let me unpack that. The naloxone blocks the receptors. So if the placebo was just imagination, it should still work.
You'd think so.
But because naloxone stops it, that means the placebo was working via opioid.
Precisely. It proves that the placebo effect is a biological event involving natural painkillers. Expectation creates biological reality.
We have to close with the evolutionary arms race mentioned in Section 4, because this, to me, is the ultimate proof that pain is just chemistry.
The grasshopper mouse versus the bark scorpion. This is from figure 8.30.
The bark scorpion has a nasty sting.
Extremely painful. Its venom contains a toxin that specifically activates that NaV 1.7 sodium channel we talked about with Ashlyn. It forces the pain channel open.
So for most mammals, being stung is agony.
Agony, but not the grasshopper mouse.
What's different about it?
The grasshopper mouse loves to eat these scorpions. Over time, it has evolved a mutation in its sodium channels, a tiny structural change. In the mouse, the scorpion toxin doesn't open the channel.
What does it do?
It actually binds to the channel and blocks it.
Wait, so the toxin that causes pain in everyone else acts as a painkiller for the mouth?
Exactly. The sting initiates a local anesthetic effect. The more the scorpion stings, the more numb the mouse becomes.
That is the ultimate no you.
It's incredible, and it brings us full circle to Ashland blocker. We started by imagining a life without pain as a superpower. For the grasshopper mouse, it is a superpower.
But a very specific one.
A specific targeted one. It shuts off pain only when necessary to survive a meal.
Whereas Ashland's silence is total.
Right, and that's the takeaway. Evolution plays with these dials, turning sensitivity up for the star-nosed mole, turning pain down for the grasshopper mouse. We humans are just another setting on that mixing board. Our reality, our pain, our pleasure, it's all just the specific calibration of our protein channels.
A humbling thought. Next time you stub your toe, just remember, you aren't being punished. You're just a machine receiving a high-fidelity data packet that says structural integrity threatened.
Try telling that to your cingulate cortex.
I will, and I'm sure it will ignore me. Thank you so much for joining us on this deep dive into Chapter 8.
My pleasure.
To our listeners from the Last Minute Lecture team, thank you for tuning in. Don't forget to review those figures, the homunculus, the dermatomes, and those pathway diagrams before the exam. They are game changers. Stay curious, and we'll see you in the next deep dive.